In this video, we're going to look at taking an opportunity to just look at how some simple harmonic motion equations are actually come about. I'm going to use a nice big piece of paper here so I can show you kind of as much as I can before changing or stopping or doing another video. I'll probably do this over a couple of videos, maybe 1, 2, or 3 even, just to really get the idea going. Now, one thing that you need to know about simple harmonic motion, so simple harmonic motion, is that obviously we're going to look at this always from the perspective of a pendulum. Now, obviously a pendulum undergoes simple harmonic motion. The time period goes from there all the way back. Common misconception about pendulums is that's the time period. Nope, all the way back. And you can remember from previous studies that obviously you can get the frequency of a pendulum by 1 over the time period. So when you know the time period of a pendulum, you can work out the frequency, which is very useful. But one of the other things that you can relate this to, and there are lots of good videos on YouTube about this, you can find and you can relate and show that simple harmonic motion and circular motion are very closely linked. And actually, the motion of a pendulum can be related to that of a circle. So that when it's at its amplitude, we can say that's its amplitude there. When it's at its equilibrium, we can say its equilibrium is there. Then back to the amplitude, and back to the equilibrium. So for all intents and purposes, we've got to this situation where we can say that circular motion and simple harmonic motion can be well related to each other. And that at a position on this pendulum, say for example here, that could be related to a position here on a circle. And so we can use the circular idea to derive an equation to let us know what this position is. Okay? So looking at this circle very clearly, if we have a look and we say, okay, well, that's an angle of theta. That means that's the angle from the equilibrium. So that angle from the equilibrium is that angle theta there. And we want to know what the distance is from the equilibrium. So the distance from the equilibrium is going to be this distance right here. And we'll call that distance x. So quite usefully, we've now got a right-angled triangle. And what you'll notice about this is that this becomes a trigonometry problem. This is a z angle, as those of you will be common for have an understanding of that from GCSE, so that means that angle is also theta. So if that angle is theta, that is x. This is the opposite side, so we'll go back to some basic trigonometry ideas here, and this is the hypotenuse. Opposite, hypotenuse, and theta. So those of you who have your trigonometry fresh in your minds will remember that you've got sine theta equals the opposite over the hypotenuse. So we can obviously rearrange for the opposite, which is the displacement, because we want to know the displacement here. And so what we can do is we can say that's the opposite. So opposite equals sine theta times by the hypotenuse. Now what do all these values mean? Well, obviously opposite is the displacement. Sine theta is sine theta. And we'll actually come up with another term for theta in a little bit. But what is the hypotenuse in this case? What is that value? Well, the hypotenuse, well, look at the length of that. It's just the length that is also the amplitude. So if you think about those as lengths, the amplitude length will be the same as the hypotenuse length. So actually we can say that's times by the amplitude. And now we actually get an equation which might look like something more similar to what you're used to. And depending on your specification, depends on what letter you use for this. So if you're in kind of a standard UK system, then A will be the amplitude. Other specifications represent A as x naught. So just be aware of that. So x will be equal to A, amplitude, times by sine theta. Well, what's interesting about that is that we can actually then make this into something more useful. Think back to some circular motion equations. Theta on a circle is found from thinking about its angular velocity. So angular velocity is defined as 2 pi over t. Well, 2 pi is the radian value of a full circle, and t is the time period. So we could also say that omega is theta over little t, where t is the time to get to that point. So in this circumstance, we're going from the equilibrium to that point. And so it's the time taken to get from the equilibrium to that point. And what's really nice about this is that theta then is equal to omega t, because we've said we can rearrange this equation and get omega t. And we can replace this value now with that and get a brand new final equation. That x is equal to a sine omega t. Now, depending on your specification, depends on how much further you take this equation. Sometimes we can go a step further and write omega in terms of something else. Omega can also be written from this relationship up here. I'll just draw it over here. Omega is also 2 pi f, because remember we said all the way up here that 1 over t is f, so that means that omega is also 2 pi f. So remember, this is the angular velocity that we've got here. So you could replace this as a sine 2 pi f t. Sometimes it's written like that, and it depends on your specification what you've got in that case. And so that is one of the equations that you may have, depending on what specification you're on. Well, there's another equation that's often used in simple harmonic motion, and it is one that uses cos instead, and it's actually the identical equation, but it uses cos. So let's have a look over on this side now about what if we take this situation, amplitude is still there, equilibrium still there, and we want to know the displacement still. Okay, so we want to know the displacement. Apologies, I've drawn that a bit dodgy, so that's the displacement there. But instead of having the angle being from the equilibrium, we have the angle from, use red, use brown. We have the angle from the amplitude. Well, the angle from the amplitude is this angle right here, theta. Notice how this is different from before. The angle we had was up here. This is the angle from the amplitude. And yes, the angle from the amplitude can be replaced with omega t, as we did all the way down here. And the triangle is still the same. This is the hypotenuse, but instead of this being the opposite now, it's the adjacent. So cos theta equals the adjacent over the hypotenuse. So therefore cos theta times by the hypotenuse equals the adjacent, which we can reword as x, remember this is the adjacent, is equal to cos theta times by the hypotenuse. Now remember, the hypotenuse is the amplitude, so we can write the amplitude. And then Because we've already said we could swap out omega t for the theta, we can say that x is equal to a cos omega t. Now, this is a big difference, and we're going to make this before we finish on this video, make this point. This is the equation from the amplitude, where the time taken is the time from the amplitude. The equation we derived before, sine omega t, when the time was from the equilibrium. So oftentimes you'll see questions that say, okay, you've got a pendulum swinging from the equilibrium or from the amplitude. You need to decide which equation you're going to use based on the scenario that you've been told about. So as long as you remember that this is the one from the amplitude and this is the one from the equilibrium, you won't go far wrong. Hopefully this video was useful for you to see where circular motion ties into simple harmonic motion and where we get these equations from. There are other algebraic ways of showing how these equations come about, but I actually find it quite nice to show you on the circles as I've done here. Hopefully that was helpful. There's another video coming up about the velocity equations next.